So, Assalamualaikum warahmatullahi wabarakatuh. So, today our group will present report presentation about the industrial talk series by Post DigiCert titled The Post-Quantum Transformation of Certification Authorities. So, for the introduction, before we start, I will introduce you our group member, which is me, NURAIN AZWA binti ADHAR, and then FATIHAH binti MOHAMAD, NADHIRAH binti FAROUK, and NURAIN binti AZMI. So, this talk highlight the importance of digital trust and the role of cryptography and public key infrastructure. So, and the emerging impact of quantum computing on current security system. We will also discuss why post-quantum cryptography is essential and how organization can prepare for future cryptographic challenges. So next, I will pass to Ain.
So now I would like to talk about the digital trust. So in the past, trust was simple. So if you wanted to do a business, then you can meet the people face to face, shook hands and sign a paper. But now you know exactly who you were dealing with. So today that has changed because we work remotely. So we store files in the cloud and we use online banking because we can't like physically see the other person or server. So we need that digital trust. This is simply the confidence that our online interactions are secure, authentic, and that no one has tampered with our information. Next. So now the CIA triad. So to build this trust, the industry relies on a security foundation known as the CIA triad. So there are three main pillars, which is confidentiality, integrity, and also availability. So first is about the confidentiality. So this is about the keeping secret safe, and it ensures that only authorized people can see sensitive data using tools like encryption. Second is integrity. So this arguably the most important one for trust, and also it ensures that data hasn't been changed by a hacker during transmission. So we use digital signatures to prove this. Third is availability. So this just means the system is online and ready to use when we need it. Next. So public infrastructure, which is PKI. Now, how do we actually make this happen in the real world? Because we use a framework called PKI, and you can think of PKI as the back-end system that manages the security keys and uh, certificates needed to prove who everyone is. So it provides the authentication and encryption that keeps the internet safe. Next. And then the role of digital certificates. So this is the most practical tool in this system. And we have to think of a digital certificate like a digital passport for a person or a server. So the speaker from Post DigiCert highlighted three big reasons why these are critical. Because first, legal recognition, and in Malaysia under the Digital Signature Act 1997. So uh, a digitally signed document is just as legally binding as a handwritten one. And then automation, it allows computer systems like ERP or CRM software to talk to each other and verify transactions automatically without a human needing to check every steps. And then costs. By cost, it saves us a lot of money because we don't need to print papers, scan it, or even pay for couriers. So this is a good example they shared was the university e-scroll. Just like our own degrees here at UTM, and also used by universities like UM. So by using digital certificates, universities can stop people from creating fake degrees because the digital signature proves the degree is authentic. So before I pass my group member, I want to share my personal reflection from the talk. So in my opinion, I was really struck by how integrity the I in the CI triad because it is the key to stopping fraud. And I realized that without digital signatures, we would never know if a document like a contract or a university degree was altered after it was signed. So for me, the most valuable lesson was that cryptography doesn't just protect data, it also guarantees it. So knowing that what I see on the screen is exactly what was sent. So it is what I found most valuable. So that's all from me.
So, I will explain about the quantum threats and post-quantum cryptography. So first, the emergence of quantum computing. From the lecture, we learned that quantum computers are fundamentally different from classical computer. Traditional computer process information using bits that are either 0 or 1. In contrast, quantum computer use qubits which can exist in multiple states of the same time through superposition and can be linked using entanglement. So these properties allow quantum computer to perform certain compilation at extremely high speeds. As mentioned in the slide, tasks that would take classical computer thousands of years could potentially be completed by quantum computers in minutes. Example, such as IBM Quantum System 1 and Google's Sycamore processor, clearly show that quantum computing is no longer theoretical but an actively developing technology. So next, we will move to impact on current system. So this advancement has serious implication for cryptography. Most digital security systems today rely heavily on RSA and which are used in 99% of digital certificate worldwide. So the lecture explained that these algorithms depend on mathematical problems that are difficult for classical computers to solve. However, quantum algorithms such as Shor algorithm can solve this problem efficiently. So as a result, quantum computers can potentially break RSA and ECC encryption, fork digital signature, and compromise digital certificates. And from a certification authoritative perspective, this is extremely critical. And if encryption can be decrypted and signature can be forked, trust in the digital documents collapse. So past signed document may even lose their legal or evidently value. So we will move to next motivation for PQC. So what is PQC? PQC is post-quantum cryptography. So in another important concept introduced in the lecture is harvest now, decrypt later. So this refers to attackers collecting encrypted data today and storing it until quantum computers become powerful enough to decrypt in the future. So this creates a serious risk for a long-term sensitive data such as government record, financial transaction, and legal documents. And to address this threat, PQC or has been developed. PQC focus on cryptographical algorithms that are designed to be secure against both classical and quantum attacks. So we will move to the key challenge of PQC. However, transition to PQC is not straightforward. The lecture highlights several challenges. PQC algorithm typically how much larger key size, which can affect system performance, bandwidth, and storage. So to manage this transition, the speaker emphasized the importance of CBOM or cryptographic bill of materials. And another key concept discussed in crypto egality, which refer to an organization ability. So before I pass to group member, from this talk, I personally realized that cryptography is not static. Algorithms such as RSA and ECC, which we often assume are secure, may not remain safe in the future due to quantum computing. So through this industrial talk, I gained a deeper understanding of how quantum computing poses a real threat to current cryptographic systems such as RSA and ECC. So the concept of harvest now, decrypt later helped me realize that cryptography must be planned with long-term security in mind. And this experience showed me the importance of post-quantum cryptography and crypto egality in maintaining digital trust. And its trademark ability to relate theoretical cryptography concept to real-world industrial practice. So I will pass to the next person.
Alright, so we go very quickly for this section. I will focus on applying the concept of discussed by post-digit, specifically post-quantum cryptography, cryptographic bill of materials, and readiness assessment to a real organization scenario. This helps bridge the gap between the theoretical cryptography and real-world industry implementation. So next slide, please. So our case study focused on PKI-dependent organizations, particularly government-linked digital services such as e-filing, e-scroll system, and e-invoice platforms. So the system rely heavily on a digital certificate issued by certification authorities and currently use classical algorithm like RSA and ECC like all we know. So as highlighted in the lecture, this makes them vulnerable to future quantum attacks, especially under the harvest now decrypt later track model, where encrypted data collected today may be decrypted in the future. So next. Okay, next slide is CBOM. Why it matters. To address this risk, the lecture emphasized the importance of cryptographic bills of materials or CBOM. CBOM actually provides a complete inventory of cryptographic components used across an organization, including algorithm, keys, certificates, libraries, and dependencies. Without CBOM, organization may not even know where vulnerable cryptography is embedded, making PQC migration risky and unstructured. As mentioned by the speaker, CBOM is the foundation for effective crypto agility and migration planning. So next slide, we will move to PQC readiness assessment. Um, There's three parts: technical, operational, and governance. So PQC readiness can be assessed across these three dimensions. First, technical readiness refers to whether the organization has enterprise-grade PKI, HSM, back key management, and support for PQC capable libraries. Second, operational readiness focus on adapting certification authority workflows such as certificate issuance, validation, and lifecycle management. Finally, governance readiness involves updating policies, monitoring NIST standardization timelines, and also the aligning with national cybersecurity initiatives. So next, okay, this is the last part of the section, migration and crypto agility. In this PQC migration should be gradual. Actually, it's hybrid approaches where classical and PQC algorithm coexist, allow organizations to maintain compatibility while improving quantum resistance. However, this approach introduces performance and operational challenges, so they should be treated as a transition strategy rather than a permanent solution. Ultimately, crypto agility is critical as it enables organizations to adapt to future cryptographic changes without major system redesign or ensuring long-term digital trust. So before I end my own session, I will do my own reflection. Personally, this lecture helped me understand how cryptography concepts like PKI and digital certificates are implemented in real life and in real systems. The discussion on quantum threats and the harvest now cryptography is the most impactful concept for me, that it made me realize the importance of early preparation for post-quantum cryptography. Learning about CBOM and crypto agility also made me think that beyond theory and consider real organization challenges. So I think this session very meaningful for my learning. That's all from my part, so I will pass to my next team members.
I will present. I will presenting about challenges of PQC. First, PQC algorithms often introduce performance overhead due to larger key size and higher computational requirements, which can increase latency and bandwidth usage. Second, this performance impact is even more critical in resource constrained environments such as IoT and embedded system where PQC employment may not be practical without optimization. Third, many organizations rely on legacy systems that lack crypto agility. These systems were not designed to support algorithm replacement, making PQC integration costly and complex. Fourth, PQC ecosystem support is still uneven, while some cryptographic library provide experimental support, many lack stable, well-tested, and interoperable implementations. Finally, PQC adoption requires significant organizational change, including updates to governance, PKI, certificate management, and staff training, which slow down migrations. Next. For the last topic of this slide is future direction for PQC. In future, PQC research aims to improve algorithms efficiency to reduce performance overhead, especially for constrained devices. Crypto agile system design will become essential, allowing organizations to switch algorithms without major system redesign. We also expect more mature PQC support in mainstream cryptographic libraries and vendor products. At the organization level, clearer governance framework and best practice will help streamline PQC adoption. Finally, continue standardization and evaluation of PQC algorithms will increase long-term confidence and reduce migration risks. So before we end our presentation today, I will give the reflections of mine. So this report showed me that post-quantum cryptography is not just a technical upgrade but a long-term organization challenge. Issues like performance overhead, legacy system, and limited tooling make adoption complex. It highlights the importance of crypto agility and early planning to ensure future quantum safe security. Now I will pass to Fatihah to close our presentation.
So it's my pleasure to be conclude this presentation. So in summary, this lecture actually allowed us to see how cryptography goes beyond theory and plays a critical role in securing real digital services. Concepts like CIA, Triad, and PKI become more meaningful when they were explained in the context of industry system and national digital platform. So overall, the session strengthened our understanding of current industry trends and showed us the importance of staying adaptable and industry ready as future cybersecurity professionals. So that's all from us. Thank you so much for listening.